Before we move on to the next session, we need to do some cleanup. So first of all is to shut down two notebook kernels here. You see that the green dots on the left side of these two notebooks represents that we were using the kernel, and the kernel is still running if we don't close it. So here, click the second tab we mentioned before. You can see the two ones. Click shut down. And this will shut down the kernel so that it's no longer running, and then you will not be able to click and run this again, because now that on the top right corner you will see that it's prompt no kernel. Unless you are selecting one again, it will not be anything workable. So this will be a pure notebook for you to look at the codes and the images and the documents, but you will not be able to run it. The reason we do this is that we want to free up some memory of this poor machine, which only has 4 gigabytes of RAM, and the road network will be more stressful than the building, so we need to clean them up. Right. And also remember to delete this untitled, which we created before just to test the installation, but it's no longer useful now. Now we can open this road network light again. The first thing we are going to do is to select the kernel. Okay, it's already there. On the tutorial. Now that we are in the road network extraction notebook, we can start to walk through what we have been doing in this notebook that is different from the building ones. So to start with, we still need to load some modules that we did the same before, but just one more thing. Like here we have this network X, and this is able to help us to do some processing with the road network. It's a topological idea in the Python. So it's new. This is different from the building. And again, the Solaris package and some plotting preference. You can see that we can queue multiple cells at the same time so that we can wait for all of them to finish running. And then looking at the data here, we now have 989 tiles of 400 by 400 meter satellite images. So these are labeled as SN3, the SpaceNet Challenge 3, still in the Vegas area. So notice that the difference here is we are using 400 by 400 meter satellite images. In the building ones, if you recall, we were using 200 by 200 meters. So why are we using different chips? These images are cropped from the same satellite images. So the content of the tiles are still the same. It's just how we crop them. You can imagine that it's reasonable to look in a smaller area in a more zoom-in way. For buildings, we just need to look at multiple buildings in a smaller chip. But for road networks, we need to look at a larger extent, right? Otherwise, you won't be able to cover those blocks, which are too large to be included in the one tile. So we are using 400 by 400 meters. So I'm not the one who set these numbers. The SpaceNet Challenge was the one who actually determined this number to be appropriate. And they also write some annotations to produce the labels for the training and the evaluation. So they set the standard to be 400 by 400 meters, and then I think it's reasonable. And again, it's a 3-channel RGB image. So here we have GeoJSON rows and GeoJSON row speeds. That's instead of only one GeoJSON, we have 2 of them. The difference to the building is that in building, we just need to know the polygon position of the building footprints. But for roads, we not only need to know the position of the roads, we also need to know the speed of each road block. That's reasonable, right? We want to know how fast we can drive on this segment of the road instead of just not only the location, but also the speed. That will be helpful in terms of the navigation use case. So to help you begin with, we already converted them to masks. The mask row speed for multi-value mask for visualization only, and a multi-channel, the mask row speed MC. So it contains multi-class binary mask for training. We'll use both of them in this tutorial. And these are already converted. You already have them if you download from the S3 bucket using the commands we ran in the very beginning of the tutorial. And again, we merge the 3D LiDAR data points into the tiles so they become another different channel, just like the building. So now we are not using elevation, we're using intensity, because Elevation is a little bit helpful for buildings because we know building rooftop has different elevation than the ground level. But for roads, that won't be any difference. However, the intensity or reflectivity level will be a lot different in terms of roads, because sometimes you can imagine the roads are made of asphalt or cement. They will give a totally different behavior to reflect lighter intensity, lighter lights than the grass or dirt or other, say, buildings. That's a better way to tell the difference between roads and the surrounding environment. That's why we use intensity as our lidar attribute this time. So this will be our fourth channel. All right, so load some data directory, and then we can see here the speed conversion file is put into this file. We can take a look at what's inside this file. Speed conversion bin. Right. So you can see here we have a few levels. So burn value, and then corresponding to speed. The speed is in the unit of miles per hour. All right. So different speed are categorized in one channel. It's called channel 0, channel 1, channel 2. It means we classify the speed by its number to a certain class. Say if it's below 10 miles per hour, it's class 0 or channel 0, and then if it's between 10 miles per hour and 20 miles per hour, probably a residential road, you have a lot of stop sign around, it will be class 1, and vice versa. The one that is over 60 miles per hour are going to be the country freeway, and it's going to be the channel 6. And they're assigned different burn values. These burn values is actually the color of the representation. If we go back to the notebook here, you can see I assign color to different classes, and then after I talk in depth a lot, we can just plot it out and see what does that mean. So first image, the satellite image, lighter intensity, same as the building, but the road max now is not only a monochrome image, it's now a multicolor image. You can see that slower roads, the slower road segments are going to be the yellow, and then when the speed gets higher on the road segmentation, if you can drive faster, the color will be darker, will be more red. So the dark red here means freeway. This can tell you some information of not only the position of the road, but also the speed of the road. What we are trying to do is to predict not only to predict the information all presented in this image. However, the network is not really good at telling you the value directly. What we're doing is to make the network do a multi-class prediction. It is a bit tricky to understand from that image. So we plot a new image here. The network will try to predict 8 different classes, and for each of them, it's going to be a binary classification. Binary classification means either yes or no, just like our building. In the building detection, we have a binary. It's either in the building or out of building. Here, we have 7 classes and 1 additional one of the aggregated mask. The aggregation means that we put all of the 7 classes in front of it together to make this. So the network will try to do 8 times binary classification, and then give us the information of not only the location of the road, but also the speed. So that's what it looks like. For example, you can see this class corresponds to the freeway, and we do not have any roads that is allowing the speed limit of over 60 miles per hour in this image. And then when we combine everything together, it's going to be the last one. So without further ado, let's just do everything the same way as we did in the building notebook. So here we load the network and then trying to do inference on a sample image that we showed before. So you should be expecting to wait for a while. All right, it's done. And now let's plot it out. The same format as before. The top left is the satellite image input, and then top right is the lidar intensity. Because we select the RGB plus intensity YAML file, the config, both of the images will be input into the network due to prediction. So this should give us the best result. And this is the result. Color as speed. You can see it's a little bit blurry on the edge. It's not as confident as the other places. And you can see some breakage of the road here. Alright? And some places are not connected. Compared to the ground truth, if we look at this in this way, it's fine, right? But eventually we want to not only have a mask of the road, we want to have a graph representation of the road. Not just like we convert the buildings to polygons, we also want to convert the road mask into a road network that we can understand exactly where is the node, where is the road intersection, and what is exactly the segment, that the line that is connecting either two of the nodes. That's why we have this graph extraction and scoring. These are all packaged into a module called APLS. We can look at this. This is also developed by Cosmic Works. They use this as their magic to measure the performance in the contest to see who actually performs the best. So to simply put, we first need to convert the road mask into road graph like this. And then they will measure randomly a source and receiver, or a source and target. They will randomly see if you can get the same route, say same length and same time as the ground truth. So they actually do navigation task in the checking of the metric. If you get a really close number, that means that your graph is the same as the ground truth. Otherwise, say if you have a breakage, if you have nodes that is not connected to each other, that means you may perform not as well as the original ground truth. So we'll see in some example here, but before that, let's run this for now. All right, while it's running, we can just go ahead and take a look at the next image here. This is what I'm talking about, a graph representation instead of a mask. Because right now we can see the nodes and the segments. This is not pixel information anymore. This is a topological information that we can see. And some imperfections we can first of all see here, because of the cars, this node is not connected to the main road here, and it's obviously not right. Okay, and also this one, there's a loop that's covered by the tree, but so the network failed to connect them. That is also not wrong, because if we want to navigate from here to here, we do not have to actually go around it. We can just go from the way here. But the map did not capture it, so that's an imperfection. An APLS score will catch this for us. That's a really good metric for road network comparison, right? All right, so since we have run that, we can run this again. All right. So this part of the code, I will not go much into the details, but just know that it is going to randomly select 2 points, one as a source, one as a target, and then give you a simulation of navigation. The first one, the left image, is going to give you a minimum length route. So this is not a really good example. Let me just run it again. Right here. So the first image minimized the length of the route. Here, the length is 329.423 meters, but it's going to be considering the travel time as a less prior metric. And the right image, you can see that, the route is a little bit different now, because this is not optimizing the length, this is optimizing the travel time, because we are considering the speed into this whole navigation. You can see that we first take a route, a small segment of the route along the fastest road, and then go into the target straight. But here, because we want to minimize the length, so we are taking this more zigzag way into this. But you can imagine that you will be driving much more slower on this road, this residential road, than this main road here. So that's the difference. We're going to use this kind of navigation simulation to measure to measure the performance of road network extraction and then compare this against the ground truth. If we can have very close simulation results to the ground truth, that means our network is pretty good. The graph has the same or very close topology as the ground truth. Otherwise, that means that we have some serious problems. So just imagine that if all of these rows are displayed, but all of them are not connected correctly, that's still not useful. We want to know the connectivity between rows, not only the position of them. It's not like a building. We just need to know the building location. Here, we need to know exactly the connectivity between road nodes. Right. So here is the scoring parts, this exciting parts. Just like when we have the F1 score measuring cells in the building notebook. Here we're going to give you a metric. It's called min.mp4, and then with the length as the weight. So we will have two scores here. One is measured with length, so this one is ignoring the speed. Another one is the travel time. It is going to consider both travel time and the both speed and the length of the road. So this one is more challenging. So naturally this score is a little bit lower than the length score. So with both of these, we can measure the performance of the result. Right. We can do some inference on random image, just like the building detection. Here, run it again. Just a few seconds. Okay. So here's the result. If we compare, it's pretty close. If we're going to compute the score of this should be pretty much perfect, because we saw everything, and the speed is correctly depicted. It's just that there is a small segment of rows that are kind of missed in this picture, but it's also really challenging, right? It's just a small pixel. So that concludes our showcase of the road network, the light version. And next we can go into the full version to see what about the training and then the full batch inference scoring. So let's look at the last notebook we're going to see today, the full version of the road network. Let's just see what's the difference between this one and the light version. Again, some introduction, and then we have this training set up. So just like the building one, we split the data to two parts by 30% and 70%. So in total of 918 images in total, we select 652 of them for training and 266 for testing. So this is a fake testing data. We know the answer of it, but we pretend that we do not know of it. We only use the 652 to train the model. Here's the training config, and this is the trainer. So it will take longer time. So remember that the buildings take about 1.5 hours to train on the P3 machine, but the road network will take longer because we have a larger input and then inference. So very similar result. And then this navigation. So this is another random selected point. All right, here's the difference. We do batch inference and all test data on all those 266 images and then get their average score to see what's the difference. So you can see that the score is like this. This is our final score. We did not compare this directly to any previous contest because this is too far away different. We do not have exactly the answer to all the other cities because in those cities, in those area of interest, we do not have LiDAR data available yet. But that's why we have to put this on as a standalone score just for reference. So 0.63 with only length and 0.585 when we consider the travel time. So next, we cannot even see how to reproduce the figures in the paper. This is the part of it. We select those sample images and plot the result of it, and then you can see the performance of the network is pretty close. A quick summary for the second session, road network detection. We have 918 merge tiles in total, and again, we split them by 70% and 30%. So the network will learn to predict the 8 class road masks. The first 7 binary masks shown here represent road corresponds to 7 beings of speed within 0 to 65 miles per hour. For example, the first one corresponds to the slowest one from 0 to 10 miles per hour, and vice versa. The last one will be any speed over 60 miles per hour. The 8th mask, the bottom right one, represent the aggregation of all road masks. So these convert our problem of trying to predict road speed to multi-class binary segmentation problem. This is more suitable for a deep learning machine model. And then our network model used in this problem is UNet with ResNet 50 backbone. And it took about 2.2 hours to chain for 100 epochs on P3 8 times large instance. Here are some examples you've seen in the full notebook and also in the paper. So we used average path length similarity, the APLS metric score. And this metric is used in SpaceNet road challenges because APLS consider both logical topology, which is the connections within road network, and physical topology, which is the locations of the road edges and nodes. The APLS can be weighted by either length or travel time. Higher score means better performance. In this case, the RGB and LiDAR combined model achieves the best score. While we can see that the LiDAR intensity doesn't score that bad, it's just a few scores different than the RGB model. The key takeaway of the whole tutorial session in this work is that we leverage AWS Open Data Registry and Amazon SageMaker to implement an idea that improves performance from a state-of-the-art baseline. And so the baseline, it was basically who won the competition. And as for the application, the work shows that while LiDAR data is more flexible to acquire than satellite images, it can also provide you information as useful as LiDAR to deep learning geospatial models. And furthermore, if you combine both, you can achieve the best score. As for future works, we would like to test models on other areas of interest with either RGB or LiDAR data using this same model. And also we want to implement LiDAR file processing on AWS directly from S3 to SageMaker to put this in a more packaged pipeline so people can try this with easier accessibility to the data. So that's all. That ends all of our tutorial for today, and we really hope that you learned something and then can innovate some ideas based on what we did. And then we would like to stay here for a while and then answer your questions or suggestions. And thank you for your attention.